Hey guys, welcome back. So today we are going to review yesterday's lesson on 8.7, which was the different special patterns with factoring. So we did the difference of two squares pattern, and then we went over the sum and difference of two perfect squares. I believe that's what it was yesterday. So we're going to review that a little bit today. This way, hopefully it'll kind of solidify those special patterns. So I'm just going to use this worksheet here. Feel free to print it out and do it along with me, or try it on your own and then watch the video after and just make sure that you did it correctly. Those would be the best ways to kind of teach yourself, so to speak. Okay, so basically we have the two different types of patterns. So the difference of two squares was the first pattern that we talked about, the difference of two squares. Now, the difference of two squares, difference basically means subtraction, right? So there has to be a subtraction sign in the middle. If there's an addition sign, automatically disqualifies it from being able to use this pattern. And then you need to have two things squared. They can be variables or numbers, or some combination of the two, but they have to be perfect squares. So if it's a variable and has a square, it's pretty obvious it's a perfect square. If it's a number, then remember I gave you that list in the notes yesterday, but basically like 2 squared is 4, 3 squared is 9, 4 times 4, 16, 5 times 5, 25, 36, 49, 64, 81, 100, and so on. Okay? So taking a look at number 1, you want to make sure that you have a subtraction sign, first of all. If it's an addition sign, no solution. The first term is something squared. This is an x squared, which is a perfect square. And then this is a 36, which is also a perfect square. So basically then, using this pattern, you're going to divide up that variable into its two x's. You're going to have opposite signs, and the 36 would be broken down into 6 and 6. So for number 2, same idea here. Okay, we have the subtraction sign in the middle, which is definitely a must. 25 is a perfect square because it breaks up into 5 and 5. 144 is a perfect square, and you could check that on your calculator. Anytime you're not sure if a number is a perfect square, if you go into your calculator and you do the square root of that number, so like 144, if you get a whole number answer like we did here, 12, you know it's a perfect square and it can be broken into 12 because 12 times 12 is 144. A number like 25, which you probably already know, is a perfect square because 5 times 5 is 25, right? So 25p squared will break up into 5p and 5p. Of course, our two signs are going to be opposite, a minus and a plus. Doesn't matter which one you put first and second. And then the 144, as we did on our calculator, we know that breaks into 12 and 12. And that would be our factorization for that problem. Now again, before you do any of these problems, even if the numbers are perfect squares, you should always check for a GCF. And I'm going to show you why in number 3. So when you take a look at number 3, you might be like, oh, well, 4 is a perfect square because 2 times 2 is 4, and 100 is a perfect square, so 10 times 10 is 100. So you could technically just factor it right away, but it won't be factored completely because you can first divide by 4 and take out that GCF of 4, giving you b squared minus 25. Then you would finish factoring that into b plus 5 and b minus 5. If you had just done it with the original problem and you didn't do the GCF, you would have had 2b plus 10 and 2b minus 10. Now, it's not wrong, but it's not finished because 2 and 10, you could take out a GCF of 2 in each of these parentheses, and you'd have to divide out your GCFs and then put that in the front. Now, if this was an open-ended type of quiz where I was checking all your work, you wouldn't get it all wrong. If you did that, you'd maybe lose a point or something for not doing the GCF. But if it's a multiple choice question, the right answer will only be this one here because that one's factored completely, and that's what you will need on like a quiz or a test. So always check for a GCF first no matter what, because it's a lot easier to do it in the beginning than the end. So same thing for number 4. What is our GCF on number 4? Well, 36 and 81 are both perfect squares. However, they're both divisible by 9. So you want to take out that GCF of 9 first. When you divide each of these by 9, then you have 4m squared minus 9. And then you can finish factoring that because 4 and 9 are still perfect squares. So then we can do 2m plus 3 and 2m minus 3. Again, if you did 6m plus 9 and 6m minus 9, not wrong, but not finished. It's not completely worked out, so would not be there if you were doing a multiple choice quiz or test. So always check for that GCF before you do any factoring. Okay, so in number 5, you have to take out a GCF because you can't, 2 and 32 are not perfect squares, so that wouldn't be an option. Anyway, plus as of right now, you'll notice this is a plus sign, so even if 2 and 32 were perfect squares, you still wouldn't be able to do that problem. So far, all we can do here is take out the GCF. Now, when you have a GCF, in this case, our GCF would be 2, but remember, whenever that lead term is a negative, you want to take the negative out with it. So you're actually going to divide out a negative 2. Now that's important because then that gives you positive x squared minus 16, and now you have the minus sign in there, which makes it a difference of 2 squares problem. So you can now break that up into x and x plus 4 and minus 4. Okay, number 6. So again, you want to divide out a GCF of 4 here, and because that lead term has a negative on it, you want to take out a negative with that GCF as well. So you're dividing by negative 4. That would make this positive r squared minus 25s squared. Then, because r is a perfect square and 25 is a perfect square, you can then finish factoring this because there's the minus sign in the middle. So you have r and r plus and minus, and then 5s and 5s. Okay, so now we're looking at those perfect square trinomials. So the big thing you'll notice with all of these, in order for them to work, there's a couple things that have to happen. Number 1, this sign here at the end has to be a plus 100% of the time. Whatever sign is in the front, that's the one that's going to go in your answer. The other thing is both the first and the last term have to be perfect squares. So if it's already a y squared, we know, okay, there's a y being squared to get y squared. The 144 had to be a 12 squared. And again, you can use your calculator and do that square root like I showed you before. Square root of 144 equals 12. So that's how we know it's a perfect square and what it equals. And then what we're going to do is we're just going to write one parenthesis. We're going to put in that y. We're going to put in that root of 12. Whatever sign is here, which in this case is a plus sign, is going to go in the middle, and then you're just going to square it. So it'd be y plus 12 squared. Okay, again, you want to take out GCF, so always look for that first. So now number 8, 9, 24, 16, there's no greatest common factor that can be divided out there, so we don't have to worry about that. We do know that these are perfect squares, and there's a plus sign here. So this is really 3c squared. This one at the end is really 4 squared, right? Because 4 times 4 is 16. 3c times 3c would be 9c squared. So we're going to put in our parenthesis 3c and then plus in the middle because of that sign there, and then the squared on the outside. So it's 3c plus 4 squared. All right, so then the next one, number 9. Okay, again, checking for the GCF first every single time. You don't want to forget that step. It's very important, but there's no GCF here. 25 and 4 are perfect squares. So what is the roots of those? Well, 5 times 5 is 25, so that's really 5 squared. And 2 times 2 is 4, so that's really 2 squared. So in my parenthesis, I'm going to write 5w and 2, and this is a minus. n squared. So 5w minus 2 squared. Okay, number 10, once again, checking for that GCF. It looks as of right now, when I take a first look at it, 16 and 49 are perfect squares, but there is no GCF, like 7 doesn't come out of 16 or whatever. So I do have the 2 perfect squares though. So when I go to do this problem, what number squared is 16? Well, the square root of 16 is 4, so that's really a 4n squared. 49 is really a 7 squared. So in your parentheses, you're going to write 4n minus 7. The minus is because the problem has a minus as its first sign, and then squared. Okay, number 11, GCF. Okay, this time we do have a GCF. We can first of all divide all of these by 2, and also the lead term has a negative, so we want to divide out a negative as well. So when you take out the negative 2, we're left with positive 9a squared, positive 6a in the middle, and plus 1 at the end. 9 and 1 are both perfect squares, so we can now continue with this problem. So this is really a 3a squared. That's where the 9 came from. You get 1 by doing 1 squared. So in your parenthesis, you're going to do 3a and a 1, but you're going to get a plus in the middle because that was the first sign of this portion here. And then just don't forget to stick that GCF on the front. So when you do divide by GCF, make sure that goes on the front of your answer as well. Okay, so number 12, 20 is not a perfect square. 245 is not a perfect square either. So the only way we can do anything here is by dividing out some kind of a GCF to make the numbers a little bit smaller and more manageable. So let's see. Let's try doing a 5 because I know that this one ends in 5. So let's see if we can divide out a 5 here. So that will give me 4z squared minus, I believe, 28z plus, and that's going to be 49, I believe, which works out perfectly because now 4 and 49 are both perfect squares. So this was really like a 2z being squared. This is really like a 7 being squared. So what is that going to look like? 2z minus 7 squared, and then just stick that GCF that we divided out on the front. Okay, so now we're just going to use this method to help us solve some problems and find some solutions. So the factoring part, you can use any of the patterns that we just did yesterday and today, or you can do some of the old factoring methods we learned prior to spring break. It doesn't really matter as long as you get the factors, because then you're just going to solve each factor. So you want to make sure it equals 0 first. Like if the equal sign's in the middle of the problem somewhere, you want to get everything to one side. So first of all, for this one, there's 2 ways we can look at it. Well, we see the x, you could just go ahead and do like the way that we learned originally, right? Where you do x and x, what 2 numbers multiply to 49 and add up to 14, 7 and 7. But if you do the new way that we just learned yesterday and today, you would see that 49 and x squared are perfect squares. So you would just go right to x plus 7 squared. Okay, so for this one, it doesn't really matter. You can get there either way. And because the 2 factors are the same, you only have to solve it one time because you're going to get the same answer either way. So you're only going to have one answer for x, and that is negative 7. Okay, so now for number 14, the equal sign right now is in the middle of the problem, and that's not really going to work for us. So the first thing we want to do is bring that 50 over. And because it's currently a positive, we're going to subtract it over. And now our problem equals 0. Okay, once you get your 0 all by itself, you want to check for that GCF. So here, 8 and 50 are both divisible by, let's see, 2. So if I take out a 2, I'm left with 4w squared minus 25. That is now the difference of 2 perfect squares, so I can actually factor that a little bit more. So I can do 2w plus 5 and 2w minus 5. Now, any of the factors that have a variable, I have to set equal to 0 and solve them to get those solutions. So my two factors are set equal to 0. I subtract 5, divide by 2. I get W equals negative 5 over 2, or you could have negative 2.5. Then on the other one, it's going to be the same thing with the opposite sign. So you get W equals positive 5 over 2. So those are my two answers for that one. Okay, so now when we go down to number 15, this is going to be like, first of all, there's no GCF, so we can't take anything out there, so we don't have to worry about that. It already has equals 0, but I do notice that 64 and 1 are both perfect squares. So I can use my little shortcut here. So I know the square root of 64 is 8, because 8 times 8 is 64. I know 1 times 1 is 1. So my shortcut here is just going to be 8p minus 1 squared equals 0. Now that would mean that I have two factors that are the same. They're both 8p minus 1, so I only need to solve one of them. So I set it equal to 0, and I solve for that variable. So 8p equals 1, divide by 8, p equals 1 over 8. And that would be my answer for number 15. Okay, so then going to 16, this one already has an equals 0, so that's good. Now we got to do GCF. So if I'm looking at these two, I believe 8 is going to divide out evenly from both. So I would be left with a squared minus 9. Now that's great because both of these are perfect squares and they have a minus sign in the middle. So that means that I can break it up as a difference of two squares pattern. So I'm going to have the opposite signs here. That happens when there's no middle. And the 9 is going to be 3 and 3. Now I have three factors here, 8, a plus 3, and a minus 3, but only the ones that have the variables need to be solved. And I end up with a equals negative 3 and a equals positive 3. All right, a couple more. Okay, so number 17. So for number 17, first thing we're going to do is divide out of 3 because there is a GCF here. So that's good. It helps us, makes our numbers smaller. So when I divide out the 3, I'm left with m squared plus 10m plus 25. Now the first term and the last term are both perfect squares. So that means I can use that little shortcut. So that means I'm going to have m plus 5 squared. Now I only have to solve that one factor because 3 doesn't have a variable and I don't need to do m plus 5 twice because it's going to be the same thing. And I get one solution, which is m equals negative 5. Okay, number 18, I can divide all of these by a GCF of 4, and because there's a negative on that lead term, my GCF is going to be a negative 4. So we divide out the negative 4. We're left with positive y squared minus 8y plus 16 in the parentheses. Both my first and my last term are perfect squares, so that means that this is really a y squared, right? This one was really a 4 squared. So that means I'm going to have y minus 4 squared in my parenthesis there. And then I only have the one factor to solve. Since I got the same one twice, I don't have to solve it twice. So y equals positive 4. Okay, number 19. So this one here, it's only two terms. Right now, 5 is not a perfect square, and there's a plus in the middle, so it looks like I can't do anything. But once I divide out my GCF of negative 5, that actually leaves me with positive x squared minus 25, which now I have a difference of two squares type of situation. So because 25 is a perfect square, I can break it up into a positive and a negative 5, and I can put in my x and my x. And then I would just solve those two, and I would get two solutions, x equals -5 and x equals +5. Okay, number 20, again, we're going to divide this one out by a GCF of -7. That's going to leave us with positive r squared minus, I believe that's a 20r, plus a 100. Now at this point, r squared and 100 are both perfect squares. So in my parentheses, I'm going to have a r and just a 10, because 10 times 10 is 100, and then that sign right there is the negative, so I have to put in the r minus 10. There's only one factor for me here to solve, which is the r minus 10. I don't have to solve it twice because I'm going to get the same answer both times anyway, so my answer there would just be r equals 10. All right, number 21. So this one, I have a GCF of 6. Take that GCF out. I have 4w squared minus 4w plus 1. That's great news because both the 4 and the 1 are perfect squares. So then that means that I can break this down into a square of a binomial. 2 times 2 is 4, so it's going to be 2w. 1 times 1 is 1, and then this was a minus sign, so that's what's going to go in here. And then I just solve that one factor, the 2w minus 1. I add the 1 to both sides, divide by 2, w equals 1/2. Okay, then I'm going to go ahead and do 22. This one looks like, let's see, is there something that's divisible by? Definitely going to be divisible by 2, so let's try that. Take out a GCF of 2, we're left with 9n squared plus 30n plus 25. Both 9 and 25 are perfect squares, so we can use our pattern. So 3 times 3 is 9, so it's going to be 3n. 5 times 5 is 25, so that's going to be 5. And this is a plus sign here, so that's what's going to go in the middle, and then that's squared. And then I just have to solve that one factor by setting it equal to 0 and solving for the n. So 3n equals -5. N equals -5/3. All right, so I think we got 2 left here. These are a little bit crazy with these fractions. I wouldn't give you anything on the quiz or anything like this, but just for a little challenge, anytime you see denominators, the best thing to do in an equation, in my opinion, is just multiply by that denominator to get rid of those fractions. So if I distribute a 2 here, I'm just going to be left with 25x squared because the 2's would cancel. Then 2 times 15 would be 30x. And 2 times 9 over 2, the 2's would cancel and you'd have that 9 again. Okay, at this point, you'd look for a GCF, but there isn't one. However, 25 and 9 are both perfect squares. So I can do 5x and 3 with a plus sign in the middle, squared equals 0. And then I would just go ahead and solve that one remaining factor by setting it equal to 0. So I would have 5x equals -3, x equals -3/5. And our last problem, again, we have a fraction. So what I would probably do is just multiply by 16 to get rid of it. Now 16 times 4 is 64. And when you do the other side, the 16s will cancel and I just have 9. Now I need to move my 9 over because I need it to equal 0. So 64x squared minus 9 equals 0. And now we can see that this is a difference of 2 squares because 64 is a perfect square. 8 times 8 is 64. 9 is a perfect square because 3 times 3 is 9. And we do the opposite signs because there's no middle term. Then you would get your 2 solutions, which would be -3/8 and +3/8. Okay. So I will be hosting, either Mr. K or I will be hosting meetups. So check in to ask questions or message us on the Remind. and have a great day, guys. See you tomorrow.